So the last speaker of this conference is Nir Avni from Northwestern, who will speak about push forwards of
push forwards.
Secret measures about polynomials. Right?
Okay, thanks. Okay. So I should mention this is joint work with Rami Eisenbud. From Weizmann Institute. It started, like many things do, with the question of Alex Lubotsky, who really likes lattices. So he's looking at following lattice and any. Yes. Is this good? Yeah. And it's a fact of life that for every n, this group has only finitely many representations of dimension n up to isomorphism. And about 15 years ago, Alex Lubotsky asked, well, how many? Okay, so if you look at question. If you look at, let's say, n-dimensional, irreducible representations of this group, the question is how many are there? Okay, how does it grow as n goes to infinity? How does the asymptotic depends on d, on the lattice itself? And he gave a few answers, okay, a few hints about the answer. With Ben Martin, they proved that this is this grows polynomial in n. Okay, this is less than some constant times n to the 3d squared. And with Michael Larsen, he proved that. So this tells you it grows at most polynomially. With Michael Larsen, he proved that it actually grows polynomially. It's bigger than or equal to n to the 1/15, independent of d. Okay? And the question is, can you do something better, to lower the gap between these bounds? But they did something more in these two works. They reformulated the question as a question about a different group, a compact group. Okay, so I remind you, there's a very famous theorem of Weil that says that representations of, so if you look at irreducible representations of SL, let's write it here. If you look at irreducible representations of SLNR, which might be a complicated object, this is in bijection with irreducible representations of some compact group. Okay, this is SUN. Okay, and what they proved is some generalization. This so bijection that preserves dimension. Okay, every representation of SLNR is actually a representation of SUN. Okay, and these two works showed that some generalization or a different form of this, some Weil group on steroids, that says that representation of SL and Z are in bijection with representation of some adelic group, compact adelic group. So SUN times the product over all primes of SLD, SLN, ZP. Okay, and so if you want to count these guys, it's enough to count representation of this group. Okay? Now, representation of SUN we know quite well. So the real question is counting representations of SLN ZP. Okay? And this is what I'm going to concentrate, and then you need to lift the information back. Okay, it turns out, so I want to give you a probabilistic version of this question, of this counting question. Okay? And it goes as follows. And this is how I'm going to use so let's call this group G from now on. And I'm going to use the compactness of G. Compact groups have Haar measure. Okay? So I'll denote it by lambda G. And what I'm going to look at is another question that group theorists are interested at. So you look at the commutator map. Okay? And let me rephrase it. You look at a random commutator. Okay? What do I mean? I'll write it in symbols. So phi1 is the map from G squared to G that takes a pair to its commutator. Okay? And you're performing the following trick. You are randomizing two elements of G according to the Haar measure independently. You apply a commutator. You get a random element of G. Okay, so let mu be, I'll write it in symbols, but this is, you're taking the Haar measure on G, but actually the Haar measure on G squared. Okay, and you're pushing it forward with respect to this map, the commutator map. Okay, this is the distribution of a random commutator. Okay, so what kind of measure do you get? Okay, if G was a billion, you would get the delta measure at the identity. Okay, this is not the case. G is not a billion. You'll get something interesting. But whether it's singular or not, okay, turns out that this measure is absolutely continuous with respect to the Haar measure. Okay, so you get some density. Specifically for, I'm talking about the SLN. You can take here any semi-simple group scheme. Okay. If you have some abelian, if you have some center, that would kill things. Oh, sorry, some abelianization that would have to factor 3. Yeah, so it means that there is some function such that mu is function times the Haar measure. Okay, this function generally is in L1. Okay, and it's not continuous. Okay, something this density tends to infinity as you go to 1. There are too many pairs of elements that commute to something close to 1. Okay. Turns out I'll indicate why. This is in a few minutes. So a natural question would be the following. If you take a measure, usually if you take a singular measure and convolve it with itself, it becomes smoother. Okay? So you may ask, you can look at, so mu is not smooth. Okay, it's absolutely continuous, but the density is not continuous. Okay, but you can ask about this measure. Okay, you convolve it with itself. Is it now the case that the density is flat? Okay, is continuous, or if not, is there some k such that this convolution has continuous density? Okay, and it turns out that these two questions are really the same. Okay, and that is, in one word, I'll explain it better, but in one word, there is, if you ask your analyst friend, they will tell you that you can test the smoothness of a measure by how fast does its Fourier coefficients decay at infinity. Okay? So what I'm going to do is I'm going to look at this convolution and take its Fourier transform. This is a conjugation invariant measure. Okay, mu is conjugation invariant. So you can take its Fourier transform. Okay? And it turns out, this is a computation that you need to do, is that, and was actually done by Frobenius, that if you look at the Fourier transform of this random commutator measure at a given character, turns out to be 1 over is the dimension of chi. Okay, which means that if you take the kth convolution power of mu, you get this is 1 over chi 1 to the 2k minus 1. Okay, that's a convolution theorem in non-abelian groups. Okay, this is why you get tier 2. Yes. And minus 1, you know. Okay. So what does it mean? Okay, so you can so you can write a function or a measure in terms of its Fourier coefficients, right? So if there is a density at a point G, should be the sum.
This is the notation for the corresponding F?
Yes, this is the Radon-Nikodym derivative, yes. Oh. Yes, this function. Would be the sum of 1 over chi 1 to the 2k minus 1 times chi g. Okay? So if you plug in g equals 1, you get that the density at 1 is equal to the sum of chi of 1 divided by chi of 1 to the 2k minus 1, so chi of 1 to the 2k minus 2. Okay? Let me rewrite it. This is sum over all irreducible characters of G. Let me rearrange the sum according to the dimension. This is how many irreducible representations of dimension n times n to the 2 minus 2k. Okay? So if the density exists, if this converges, now this is an infinite sum. If this converges, it means that the general term has to grow slower than this number. Okay? So this is more or less the relation between these two questions. Okay. Okay. So here's the question. You get a measure. You want to know how you're looking at this measure. You want to know when does it have a continuous density. Okay, some push forward has continuous density. Again, I'm going to massage it a little bit. Instead of talking about convolutions of a given measure, I'm going to write phi of k to be the map between g to the 2k to g, sending x1, y1 up to xk, yk to the product of the commutators of the pairs. Okay. Xk, yk. Okay, and this mu convolution k times is equal the push forward of lambda to the g to the 2k. Okay, so I prefer to talk about one push forward and not convolutions of it. Okay? Any questions? Okay, so this is a part of a more general question. Okay, you have a variety x, you have a variety y, you have a map between them, and you want to know a polynomial map between them, and you want to know, and you have some measure here, and you want to know when is it true that you can push forward. And what you'll get is a variety with a measure with continuous density. Okay? So let me write it. So let's replace the variety. This is, I'm not limiting the generality, really. So suppose that f is a map, is a polynomial map, okay? an to am, polynomial map. Let's say over z, okay? And I'm asking when is it true? So under what condition on f? That for every prime number, if you look at, if you now apply this map and plug in zp numbers. So if you look at lambda of zp to the n and push it forward according to f, okay, now this is a measure on zp to the m has continuous density. Okay, you can ask other questions. For example, a more basic question would be, when is it true that when you push forward this constant measure, you'll get a measure that's locally constant? Okay, or when is it true that when you push forward this measure, you'll get a measure that's absolutely continuous? Okay, let's start with this. Okay, so it turns out that you'll get an absolutely continuous measure if and only if this map is dominant. So if you map into a subvariety, you're not going to get. And it turns out that if you don't, if this obstruction does not exist, if you're not mapping into a subvariety, then you automatically will get a measure with density, with L1 density. Okay. So L1 density is equivalent to f being dominant. Okay. If you want locally, how?
You need some kind of. This is trivial, or you need some kind of theory? You need to know how to count points?
It's no. It's totally. You need the fact that a dominant map. Give me a second. I'll write something here that will imply this. You can ask whether the push forward divided by lambda, so the density is locally constant. It's locally hard. Okay, which you start with a measure that's locally hard. Okay, and you push it forward, and you want to know when is it locally hard. Turns out this is equivalent to f being what algebraic geometers called smooth map, but are called submersion. Okay, the differential is onto at every point. Okay. Okay, now the claim is that the dominant map is a submersion outside, generically a submersion. Okay, that is why this result implies this. And this is an easy result. Okay. That's basically linear algebra. Okay, but the question we ask is something stronger. Okay, something in between. We want to. It's more delicate. You want something that's not locally hard but continuous. Okay, so you should relax this condition. Okay. Now, submersion in algebraic geometry, smooth map in algebraic geometry, is the same as f being flat and the fibers are smooth. Okay. It turns out that you cannot relax the flatness condition, but you can relax the smoothness condition. Okay. So here's the theorem. Let's call it this condition star. Okay. Star holds if and only if. Okay, so there is a characterization, and more than that, it depends only on the fibers of this map. Okay, if and only if all fibers of f have the following three conditions. So they should have the same dimension. And this is flatness. Okay, map is flat. A map between two smooth varieties is flat if and only if the measures of the dimension of the fibers are constant. Okay. The fibers should be reduced. Okay, so I'll write it that have multiplicity 1. Okay, so for and 3, and this is where I'm going to cheat you a little bit. All of these fibers have only canonical singularities. Okay, so canonical singularities is a known notion of singularities. Okay, I'm not going to define it. Here I'll say something. I'll give an equivalent definition if we have time at the end of the lecture when I explain the proof of this theorem. But it's some kind of mild singularity condition. Okay, so let me just give you an example. If you look at the map, z goes to z squared, okay, one dimension, you'll see that this condition does not hold. Okay, the push forward of the hard measure on zp is not going to have continuous density. Okay, and that's because it violates the multiplicity 1. There is a single point, 0, where the multiplicity of the fiber is 2. Okay. Something that.
But can you say it on the density level?
Yes. What do you mean, that the multiplicity is 2 and not 3?
Explain why star is violated and directly without the theorem? In this
Proving this direction? Proving this direction?
No, in this specific case.
I can show you why the. What are you asking?
Can you show me without the theorem why it's not continuous?
Yes, of course. So you ask yourself, what is the probability? You randomize a p-adic number. What's the probability that it will have valuation r? And then you want to divide it by the volume of all elements, or by the annulus of radius p to the r, p to the minus r, right? So the set of all points such that z squared has valuation, has norm p to the minus r, well, it depends on whether r is even or odd. If it's odd, it's 0. But if it's even, let's put here 2r. Okay, you want the Haar measure of this, divided by the Haar measure of z such that the absolute value of z is p to the minus r, right? But this is just the condition that, sorry, 2r. Okay, and this is just the condition that the absolute value of z is p to the minus r. Okay? Okay, but this is each one of them. This is roughly p to the minus 2, p to the minus r. This is p to the minus 2r. Okay, so the density at a point of radius p to the r is p to the 2r. So this is 1 over p to the. So it's p to the r, yes. And this goes to infinity as r goes to infinity.
Yeah, so it's explodes at 0.
Yes. So it's continuous except for 0, which you knew because outside 0 this map is a submersion, and it will explode at that point. Okay. As another example, the commutator map. Okay, you can see that generically, if you want to know how many points, how many pairs of elements that whose commutator is a random matrix, is this is a d-dimensional variety. It has the dimension of G. But if you're looking at pairs of points that commute, okay, so you're looking at the commuting variety. This has dimension bigger than the dimension of G, right? Because for every point in G, it has a whole positive dimensional variety, usually the rank of points that commute with it. Okay? Okay. So maybe I'll make a digression because this also connects to I think a more basic question of counting solutions to algebraic equations. Okay, let me just give you the connection. If you have this map, okay, a map between AM and AN, and you look at the 0 locus. Okay, let's denote it by X. Okay, and you're looking at the push forward of the Haar measure on Zp to the n. Okay, this is a measure. You want to know what it does, what it gives to p to the a, Zp to the m. Okay, this is a measure on Zp to the m. You're looking at a small ball, and you want to know what this measure is. Okay. And this is equal to better. No, let me write in this way. This is p to the minus an times the number of solutions of x in the ring Z mod p to the a. And that's the point is that what is this? This is the usual Haar measure of the pre-image of p to the a Zp to the m. Right? So you are looking at all points in Zp to the n, such that when you apply f, you get something that's divisible by p to the a. Okay? This is a union of balls of radius p to the a. If you take such a point that maps, whose image is divisible by p to the a, and you perturb it a little bit by something of, you perturb it by less than p to the a, it will still satisfy this condition. Okay? So this is going to be a union of balls of radius p to the a. This is the measure of each one of them. And how many of them? They're going to be exactly this number. Okay? So such a condition, push forward, has bounded density, tells you something about the relation between this measure and the Haar measure of z p to the m. Okay? So I'll do the translation for you. Get the following theorem. So this is a corollary of this theorem. Let's suppose maybe before that, if you have a scheme X, okay, and a finite, so an R is a finite ring, you can look at the solutions in R of X, number of solutions, and the correct, well, the first guess is what should be the correct normalization is R to the dimension of X, right? But actually it should be the complex dimension of X. It's not the dimension as a scheme, it's the dimension of the generic fiber of this. Let's call it Hx of R. Okay? So suppose X is a local complete intersection. Okay, and let's say it's irreducible and reduced. Okay, these are clear conditions. The local complete intersection is a bit dubious. I mean, this is just, I don't know to do anything better. The following are equivalent. One is that for every p, hx of z to the p to the n. Okay, so you're counting how many solutions X has in this ring and normalize it correctly. This is bounded in n. Second, this bound is independent of p.
So by scheme,
Okay.
you mean scheme of the Z.
Z scheme, yeah, finite type. There exists a constant such that hx z over p to the n minus hx of z over p is less than c over p. Okay, and by Lang-Weil we know that this goes to 0, goes to 1 very fast. Okay, so not only are these numbers bounded, they actually go to 1 as p goes to infinity, but independently of n. And 3, x, c, generic points has only canonical singularities. Okay, so this is a characterization. This is an if and only if, but it only talks about number of solutions over local rings. Okay, let me say something weaker about solutions in Z mod n, which is really what we're interested in. In this case, so if these conditions hold, So you would like to have that hx of z mod n to converge. Okay? But it's not true. It's not true even for smooth varieties, even for elliptic curves. Okay? So they don't converge, but they converge on the average. Okay, it's this limit of 1 over n hx z modulo 1 plus hx z modulo n. If you look at the averaging of the normalized count of solutions, this converges, exists, and is a number bigger than or equal to 1 and less than infinity. Okay? Oops. Questions?
Can you actually compute it in some cases?
Well, this limit? No, I don't.
Even if you know what is the constant C? Or
Sorry?
even if you know something explicit in the corollary? Like what is the constant C? Or
No, because I need to understand these numbers. And this is Galois representations and things I don't know. This is a Tate type of theorems, which I don't know about. It's a good question, but I don't know to do this. Anyway, that was a side. Let's go back to the question. This measure. Okay. So again, we have this product of k random commutators. Okay, and we want to know whether this push forward has continuous density. Okay? So a priori, we need to check all fibers of this map. Okay, we should check the dimension, the multiplicity, and the canonical singularity condition. Okay, it turns out, in this specific case, that there is only one fiber that you need to consider. Okay, there is one fiber that controls all the rest. If you prove it for it, then everything else follows. Okay, and it's not so hard to guess which fiber it is, right? Like, what's the special point in G? 1, right? So you have this phi k inverse of 1 here that you need to check the condition on it. So what is this phi inverse of 1? This is the set of all G1, H1, GK, HK, such that the product of commutators, G1, H1, GK, HK, is 1, right? So it should remind you something. This is the relation for a surface group, right? This is just the set of all homomorphisms from a surface group to G. Okay? And so it's sometimes called the deformation variety of the surface group in G. Okay, and here's the best we can do now. If k is bigger than 12, bigger than or equal to 12, then this deformation variety f sigma k SLD has. So let me just say that for k equals 1, I said it doesn't satisfy the dimension condition. The dimension is too big. Okay? But for k bigger than 1, it's true. And the real condition becomes this, the canonical singularities. Okay? So if this condition, then this deformation variety has canonical singularities. Which doesn't tell you much because I didn't tell you what are canonical singularities.
Can you explain where does 12 come from?
The way we prove it, here's the way we prove it, okay? There is a theme in algebraic geometry that tells you that if you have a family of varieties, and you're looking at one variety, and it behaves not better than nearby varieties. So if it's smooth, the nearby varieties are also smooth. Okay, it depends on what you call a family in each case, but and the same is true for canonical singularities. Okay, so if you want to prove, suppose you want to prove that a variety X has canonical singularity. We do this by taking degeneration of X. So it means a family xt over t in, let's say, c minus 0. Okay, you write down equations such that for every t except 0, this is isomorphic to X, but it extends to flatly to x0, which is defined over x0, which is not isomorphic to X. Okay, it can happen. There are plenty of examples. If you want to prove that X has rational singularities, it's enough to prove that x0 has rational singularities, again, because it will be true in a neighborhood in a small neighborhood, for t very small, but all of them are isomorphic. Okay? So we do a sequence of degenerations of this variety. And somehow we break the complexity of SLD. SLD is a very complicated group. We somehow break the complexity of this group into things that look like the Heisenberg group. But in each step of such a thing, you need to assume k is big enough. Okay. So that's. But it's a shortcoming of our proof. I think I'm pretty sure that the real theorem is about 2. Okay. So let me just state the 2 corollaries. Oh, 3 corollaries. What you get out of this theorem is that the number of n-dimensional, or at most n-dimensional, irreducible representations of SLD ZP grows is n to the little o of 22. 22 is twice 12 minus 2. Okay?
What is O little o 22?
Sorry, 22 plus, sorry. So, I mean, this is little o of n to the 22. Okay? Sorry.
But now you can't.
So if the above theorem is with k bigger or equal to 2, then this is O of n squared?
Yes. Yes. Yes.
What is the independence of the absolute? I mean, does the constant here depend on some of the parameters?
I don't know. I don't know. Probably for 22, no, but I don't.
But as you stated, D and P are fixed, and n tends to infinity.
Yes, this is a constant that depends on D and on P. Okay, slightly.
The point is that when D is bigger than whatever was in the theorem of Vygotsky and
Right. So
then Martin.
so give me same. So the n-dimensional representations of SLDZ, okay, the lattice is big O of n to the 22 plus epsilon. Now the constant here does depend on d and epsilon. Okay, but this is the generalization, the strengthening of this theorem of Lubotsky and Martin. Sorry?
What was yesterday?
Yeah, replace 22 by 3d squared. So it depends on d. This is a result that's independent of d. Okay. And let me restate it in the probabilistic claim that if you take the product of 12 random commutators, in SLD ZP, and probably also in SLDR and in SLDC, okay, has continuous density. And I'll stop here. Thank you.
Questions?
Yes.
So you said at the last moment that probably in SLDR and C, what did you mean? That it's correct or you?
Yeah, no, it's correct. So take any measure, let's say smooth probability measure with C infinity.
The point is that you don't have Haar measure.
You don't have Haar measure, but it doesn't depend on the measure.
Yeah.
It's really not a question about measure. It's a statement about measures with smooth density.
More questions? Okay, so let's speak to all the speakers of today and see you in the next conference.